Hello everyone, in this session we will explore DBSCAN, a powerful clustering algorithm that groups data based on density rather than distance to centroids. It's a very practical method for finding arbitrarily shaped clusters and detecting outliers automatically without knowing the number of clusters beforehand. So let's see how it works and where it can be applied. DBSCAN is a type of unsupervised machine learning algorithm, meaning we don't tell it what the clusters should look like. Instead, it groups together points that are densely packed and labels sparse points as noise. A key advantage is that we don't need to specify the number of clusters, unlike some other techniques like k-means, which makes it particularly powerful for messy or complicated data. DBSCAN defines three types of points. A core point has many points close to it. It sits in a dense area. A border point is near a core point but doesn't have enough neighbors itself to be a core. A noise point is isolated. It's not close to any dense group. These simple definitions allow DBSCAN to naturally separate clusters from background noise. So here is the process. First, we look around each point to see how many neighbors it has within a radius epsilon. If the point has enough neighbors, it means minimum number of points, it becomes a core point and starts a new cluster. The algorithm then expands that cluster by pulling in any points reachable within epsilon, repeating this course for any newly discovered core points. Points that don't meet the density criteria become noise. They don't belong to any cluster. DBSCAN has two main parameters. Epsilon defines the radius around each point that we consider for neighbors. Mean points defines the minimum number of neighbors needed to form a dense region. Setting epsilon too small may lead to too many small clusters or points marked as noise. Setting epsilon too large may merge distinct clusters into one. Similarly, mean points controls how dense a region must be to count as a cluster. Choosing these parameters carefully is crucial for getting good results. A k-distance plot can help pick a good epsilon value by identifying a natural threshold. Minimum number of neighbors controls how thick a region must be to qualify as a cluster. A core point has equal or greater than minimum number of neighbors within epsilon distance. Let D be the number of features actually used after preprocessing. Start around D plus 1 to 2D, but don't go below 3 or 4 so cores are not formed by tiny pairs. Match minimum number of neighbors to the smallest pattern you care about. For example, minimum broad segment group, vehicle count, parcel block. For noisy or high dimensional data, bump minimum number of neighbors up to suppress speckle. For very small, clean datasets, back it down cautiously. Use the k-distance curve with k equals minimum number of neighbors to choose epsilon at the elbow. Then run a quick sweep of epsilon and minimum number of neighbors and report how cluster count and noise fraction change to justify the setting. Before running DBSCAN, we need to choose a good value for epsilon, the neighborhood radius. One common method is to create a k-distance plot. Here, for every point, we calculate the distance to its k's nearest neighbor, where k is typically equal to the minimum number of samples. Then we sort these distances from smallest to largest and plot them. The plot typically rises slowly at first because points inside the dense clusters have nearby neighbors. Then suddenly the distances shoot up. This marks the transition from dense regions to isolated points. The sharp bend, often called the elbow, suggests a good choice of epsilon. Choosing epsilon too small would split clusters unnecessarily. Choosing epsilon too large would merge different clusters and include noise. In summary, find the elbow, set epsilon slightly larger than that point, and you are ready to apply DBSCAN with meaningful results. DBSCAN has several advantages. You don't need to specify how many clusters you want. It finds them automatically. It can detect arbitrarily shaped clusters, unlike k-means which prefers circular clusters, and it is also robust to outliers. Noise points are automatically labeled and ignored by the clustering. This makes DBSCAN ideal for real-world datasets where shapes are complex and data may be messy or incomplete. This animation shows a side-by-side comparison of how DBSCAN and k-means behave on crescent-shaped data. On the left, we see DBSCAN. It correctly identifies the crescent shapes by clustering based on density. Points close together naturally group, even though the shapes are complex and curved. On the right, we see k-means trying to cluster the same data. K-means assumes that clusters are roughly spherical. It cuts through the crescent shapes awkwardly because it tries to split the space into equally sized circular groups. This leads to poor clustering results for non-spherical data. Notice also how DBSCAN automatically detects noise points and marks them in yellow. These isolated points, they don't belong to any cluster. Now let's look into some examples where we can use DBSCAN. Imagine a city full of taxi pickups. Instead of drawing arbitrary grid lines, DBSCAN groups areas where pickups naturally concentrate. It detects real hotspots like airports, malls, and downtown zones without needing any pre-assumed boundaries. This is extremely useful in urban planning, logistics, and public safety. In fields like finance, cybersecurity, or structural monitoring, anomalies are important but rare. Because DBSCAN labels isolated, low-density points as noise, it naturally flags unusual data points. This makes it a great tool for detecting fraud, spotting unusual system behaviors, or catching early structural problems in bridges and buildings. In structural health monitoring, DBSCAN is used to analyze continuous data from sensors attached to bridges, buildings, or other structures. These sensors measure things like vibrations, strains, or deflections. DBSCAN helps group normal behavior patterns and flag unusual changes as anomalies. For instance, a sudden change in strain measurements after an earthquake could indicate earlier stage cracking or internal damage, which DBSCAN can highlight automatically. In pavement condition assessment, we are clustering surface metrics such as roughness, watering depths, and cracking severity collected by LiDAR or imaging systems. The goal is to find zones of similar pavement quality and to flag outliers that need immediate repair. DBSCAN is a good fit here because it automatically groups distress patterns and treats isolated damage as noise. On this slide, notice the example. We can detect highly damaged areas on an otherwise good highway and plan targeted maintenance instead of resurfacing the whole segment. For traffic incident detection, we use DBSCAN to cluster vehicle trajectory data or speed density patterns from smart transportation systems. The idea is that normal traffic forms coherent clusters, while disruptions separate from those patterns. By focusing on the data shown here, we can identify when conditions deviate from typical flow and highlight likely incidents for operators to review. In remote sensing and land use classification, we analyze satellite or drone imagery and cluster land surfaces into urban vegetation, water bodies, and construction sites. Over time, the same approach lets us detect changes such as unauthorized construction. DBSCAN helps because it can find natural land cover clusters of arbitrary shape and it handles mixed or transition pixels as noise. The example on this slide is monitoring urban sprawls near transportation corridors or airports. To summarize, DBSCAN groups points based on density, not distance to centroids. It can detect clusters of any shape and it automatically identifies noise. You don't need to guess the number of clusters ahead of time, which makes it extremely flexible. However, careful tuning of epsilon and mean points is important for best results.